say, let's start the seminar. It's 4 p.m. So welcome everybody to the Asia Pacific Analysis MPD seminar. And today's speaker is Joachim Kerner from the Bergische University Wuppertal in Germany. And Professor Kerner, he received his PhD from the University of London, the Royal Hello University in the United Kingdom, in 2013 under the supervision of Professor Jens Bolte. After a few months as a postdoc at the University Stuttgart in Germany, he joined the University of Hagen in 2014 as a postdoctoral research fellow. And in 2020, Kerner got promoted as senior lecturer at the University of Hagen. In 2016, he received a faculty prize for an outstanding publication. And Professor Kerner is currently as a substitute professor at the Bergische University in Wuppertal. Okay, and Joachim, I'm very happy that we could arrange a talk for you here in our seminar. Please start.
Okay, so thank you, Daniel, and also thank the other organizers in the background for having invited me. Okay, so today I'm sorry for that you cannot see me, but we have this bad internet connection problem. Okay, so today I want to speak about the spectral gap of Schrödinger operators. And basically I will present rather recent results. And part of the work is joint work with Matthias Teufel, who also joined this seminar. Okay, so let me start. Okay, so the setting is relatively simple. So we look at standard Schrödinger operators HL of this form. So we have a negative Laplacian plus some external potential V. And this operator is defined on, well, in general in d dimensions on a cube in Rd. You see here lambda L. But for most of the talk, we will focus on the one-dimensional setting. And then in the end, we move to 2 dimensions and higher dimensions. So in 1 dimension, we simply have an interval of length L. Okay, and it is important that we study non-negative potentials. And we also assume throughout the talk that the potential is bounded. So it's an element of L infinity. Okay, so I mean the underlying Hilbert space, you don't see it here, but it's the L2 space. And so in order to obtain a self-adjoint operator, we need to impose some boundary conditions. And basically we will either assume Dirichlet or Neumann boundary conditions. And I mean, in the beginning we studied Dirichlet, and at some point for some reasons I will switch to Neumann boundary conditions. And I will let you know when I do it. Okay, in any case, we have a self-adjoint operator, and since we live on a bounded domain, we have purely discrete spectrum as well. Okay, this means we have eigenvalues. So the spectrum consists only of eigenvalues, and the lowest eigenvalue we denote by lambda naught, and then the first excited eigenvalue, so the second eigenvalue is lambda 1. And this then leads to the quantity we are interested in, the spectral gap, which is defined as the difference of the first 2 eigenvalues. And yeah, let me say 2 things. First of all, it's well known that for this operator, the ground state is non-degenerate. So for each value of L, the spectral gap is a positive number. And of course, it depends on 2 things. It depends on the volume of the system, so on the length of the interval, for example, and also on the potential. And so do the eigenvalues. Okay, and then a basic question we want to study is, so how does the spectral gap behave in the limit of large interval length? So large volume. And of course, the potential matters. So the question is, how does the potential influence this asymptotics? Okay, so that's our basic question. And now, of course, I have to give you an idea. So what can we expect? So we need something like a reference. And the reference operator for us will be the free Laplacian, so where the potential is equal to 0. And this, of course, is a simple operator. It's simply the Laplacian on an interval or on a cube with either Dirichlet or Neumann boundary conditions. And so you can solve it explicitly. You know the eigenvalues and you also know the eigenfunctions. And therefore, you know the spectral gap, right? And so the spectral gap in this case is a constant divided by L squared. And the constant depends on the dimension and the boundary conditions. So for example, if you are on an interval with Neumann boundary conditions, then the first eigenvalue is 0 and the second is pi squared divided L squared. So the gap is pi squared divided L squared. And for the Dirichlet operator, you have a 3 pi squared divided L squared, right? Because the first eigenvalue is already pi squared divided L squared, and the second is 4 pi squared divided L squared. Okay, but in any case, we draw two important conclusions from this. The first is the spectral gap converges to 0 whenever you increase the length of the interval. And the second is it goes to 0 like 1 over L squared. Okay, so in this we should keep in mind. And then let me mention a different way to look at this problem, which is a very classical question, and there are many interesting papers on this. So the idea is the following. You start with an interval, and you have the Laplacian without potential, and then you know the gap, right? And then you add a non-negative potential, and you ask yourself, what happens to the gap? So does it increase or does it decrease? And well, maybe in the first few seconds you think about it, you might think that because the potential is non-negative, the gap should increase. But of course, this is it's more subtle, and this is not necessarily true, because the potential being non-negative means that all the eigenvalues go up, or at least don't go down. But of course, the first eigenvalue, so the ground state, the lowest eigenvalue could go up a bit more than the second, so the gap could still decrease. Okay, so people study this question, and there are, so it's really highly non-trivial to answer this question, but there are a few interesting papers, starting with work by Ashbaum Ben-Gurion in the 80s, and then Levine, for example, was in 94, and there are other papers by, for example, Abramowitz. And they could show something like if you add a potential that is, for example, Levine proved that if you add a potential non-negative that is convex, then the spectral gap increases. Okay. But for example, and the same Ashbaum Ben-Gurion studied symmetric single well potentials, and also for such potentials the spectral gap increases. But there was also, Abramowitz had, like in his paper, sort of a W potential, or like a Mexican head potential, and for such a potential the spectral gap decreases. So in other words, it strongly depends on the actual potential you choose. Okay, and this was basically our starting point, because we came from a, let's say, a mathematical physics problem where you don't know too much about the potential. It's wildly oscillating. And so we couldn't really use the results from these people. So we started to wonder, like, isn't it possible to maybe say something for more general potentials? But of course, you have to pay a price. Because if you stay on a fixed interval, it's not clear what to do. So the idea was to allow for more general potentials, but then to allow also like to send the volume to infinity. And as you will see, this enables one to show something at least. Okay, so now we start basically with some results. So let's start with an upper bound. So this is the spectral gap. And we know that for the free Laplacian, it goes to 0 like 1 over L squared. And okay, and then you simply recognize that. Okay, let me, of course, I have to say something about V here. So we assume that the potential decays fast enough, and this means at least like 1 over x squared at infinity. So if you look at fast decaying potentials, then you can show that the first 2 eigenvalues at least go to 0 because you increase the volume. So this is what you expect, but they converge to 0 like 1 over L squared. And so, I mean, it's trivial to conclude then that the spectral gap also converges to 0 like constant divided L squared. So this is simply an effect of increasing the volume of your interval. Okay, and now assume you have, well, you don't have to assume, but let's think of a compactly supported potential. Okay, so this is decaying very fast, of course, so you have this upper bound. And now you have your potential, and you increase the volume. Maybe I could even try to show you a picture. There is already. So you see, so you have an interval. Maybe here we have somewhere here is the 0. Okay, sorry for, and so here this could be the potential, right? V of x. And yeah, and then you make the interval larger and larger, right? And the potential just sits here. And then what you would expect maybe is that because you have a very large interval and the potential has only compact support, you don't see it in a way. So you would think that you have also a lower bound of this sort, so constant divided L squared, because in a way you should be close to the free case. And surprisingly, this is not true. So you can show the following. If you have a potential that is non-zero, so you need to have a potential, and that decays faster than 1 over x squared, so let's say 1 over x cubed, or 2 plus epsilon is enough, then you can prove that L squared times the gap converges to 0. And now again, if you compare this, for example, with the free Laplacian, then this is really different. I mean, for the free Laplacian, L squared times the gap is a constant, so it doesn't converge to 0. So in other words, for fast decaying potentials, the gap converges to 0 faster than it does for the free Laplacian. And this, of course, holds for compactly supported potentials. And this is, for us at least, this was a surprising result because, as I said, intuitively, maybe you begin with thinking like you should be close to the free Laplacian. But this is not true. And now there is a very, maybe I should go back. Okay, so it's a confusing result first. But as soon as you understand the mechanism behind it, it's quite obvious why you should have this result. So let me first describe it in words and then maybe with the picture. So there are two mechanisms that lead to this. The first is the well-known thing. So you increase the volume of your interval, and this leads to the 2 lowest eigenvalues converging to 0. And this was the reason for this upper bound, for example. So you expect at least like 1 over L squared convergence. But then you have an extra effect. And namely what happens is, since the 2 eigenvalues converge to 0, this small potential, compactly supported, sitting somewhere, becomes a higher and higher barrier. Okay, for example, if you're a particle occupying the ground state, you have very small energy, but you have a potential sitting somewhere. So this looks like Mount Everest. And in mathematical terms, what this means is the potential, in a way, appears like a Dirichlet boundary condition. So in other words, the potential leads to an effective decoupling of the interval, right? So you have your interval, and you make it larger and larger. And then here where the potential is, you basically create a Dirichlet boundary condition. And this means you cut your interval into two parts, right? So you have a left part and you have a right part. And then imagine you start from the very beginning with an interval, and then you put in the middle of the interval, you put a Dirichlet boundary condition. Then you immediately conclude that the ground state is degenerate, right? Because you have the ground state from the left continued by 0 to the right. Then you have the ground state from the right continued by 0 to the left. And this degeneracy is the reason why the spectral gap converges faster to 0 on the interval with potential, because the potential effectively creates a Dirichlet boundary condition. So in the limit, in a way, it decouples left and right-hand side. Okay. So that's the intuition behind this spectral gap converging faster to 0. And now let us continue. So now we know that the spectral gap goes to 0 faster for fast decaying potentials, but we don't know how fast. So we are interested in lower bounds. And we also put forward a small conjecture. So we think that if you have a compactly supported bounded non-negative potential, then the spectral gap should decay to 0 like 1 over L to the power 3. And we showed this for just one specific case, like a step potential. So we still believe this is true, but we couldn't prove it so far, but later I will come back to this. So what about lower bounds? Okay, and now I will tell you I have two lower bounds I can present. The first is a very general lower bound, and the second holds only for a smaller class of potentials, but it's a better lower bound in a way. Okay, but what we have to do is we have to now switch from Dirichlet to Neumann boundary conditions. So again, we have the standard Schrödinger operator on an interval, HL, which is negative second derivative plus a potential, which is bounded non-negative. And now we impose Neumann boundary conditions at the endpoint. So the derivative, the normal derivative, is vanishing at the endpoints. And the reason we do it is, basically because I want to use a result which helps me only in the Neumann case. So that's the reason I'm choosing Neumann boundary conditions here. And namely, I want to use the following result by Kirsch and Simon, which, I recommend you to have a look at this paper. It's somehow interesting. And it's also interesting because it's like they study the spectral gap, but from quite a different point of view. For example,
Joachim, versuchst du uns gerade einen Slide zu zeigen? Oder?
Ja.
Du bist noch auf deiner Zeichnung.
Oh, wow. Okay. Das tut mir leid. Okay. So sorry, yeah. So where did I miss you actually? Like somewhere here?
Yes.
Okay. Yeah, sorry for this. Okay, sorry. So I repeated. So let me just, so we understood that the spectral gap converges to 0 faster than it does for the free Laplacian for fast decaying potentials. Then we had this basic mechanism. So the combination of increasing the volume and effective degeneracy of the ground state. And now I got interested in lower bounds on the spectral gap. And this is what I want to do now. Okay, so now we are back to an interval but now with Neumann boundary conditions, and I'm interested in a lower bound to the spectral gap. Okay. And then I mentioned this paper of Werner Kirsch and Barry Simon from the 80s, where they look at the spectral gap from a different point of view. I think based on the work of Brian Davis, they establish you can write down a variational characterization of the spectral gap. And from this variational characterization, you obtain this result, which is somehow interesting. So you can, so that's the spectral gap we are interested in. And then Kirsch and Simon prove an upper and a lower bound of this form. Namely, what they say is you take your unperturbed operator, which is in our case simply the free Laplacian, and the spectral gap of your unperturbed operator is an upper and a lower bound to the spectral gap of your perturbed operator. But of course, you have to pay a cost, so you have to multiply with a certain constant here, or factor. And this factor contains the two ground states of the two operators. So as you can see here, so this is the spectral gap we are interested in. And here you see the spectral gap of the Neumann Laplacian on an interval. And here you have the minimum of the ground state of our operator with potential divided by the maximum squared. And actually, you would also expect the ground state of your unperturbed operator, but since the ground state of the Neumann Laplacian is the constant function, it drops out of this expression. So this is what you get. So now there are good and bad news. The good news is you have a lower bound, and we all know that lower bounds are somehow tricky to establish. The bad news is, of course, you have to study the ground state of your operator, and this might not be so simple. It's not quite clear. But nevertheless, if you look at it, if you have the minimum and the maximum of a function, and you want to say something about the relation, so most likely we think of Harnack inequality for phi naught. So this is the idea, to derive a Harnack inequality. And to do this, well, I came across this paper of Berhanu and Mohammed, and they study, I mean, you can read it from the title, they study Harnack inequalities for ordinary differential equations. They have somewhat a different perspective, but you can, if you read the paper, you can use their techniques to arrive at the following result. So you can prove that you have this Harnack inequality for the ground state of the Schrödinger operator. And the important thing here is, of course, it's with an explicit constant. So two things. First of all, this Harnack inequality holds for all values of L. So not only for large L, but for all L. And for all bounded potentials. And you see here, I mean, there's an L1 norm of V over the interval. But if the potential is bounded on R, then it's, of course, in every compact interval, it's in L1. So this is well defined. But if the potential, for example, is in L infinity, but not in L1 of R, then this norm diverges in this case. Okay, so. Okay, and of course, I mean, it's a Harnack inequality, so it's, of course, this constant is expected to be very small. So in a way, we will obtain a general lower bound, but quite a weak lower bound. It's very small, but nevertheless. So let me just say something about how you prove it. So basically, what you do is you start. The proof is elementary. There's sort of a trick, which you find in this Berhanu-Mohammed paper. So you start with the eigenvalue equation. This is, in a sense, the only thing you use. And using the eigenvalue equation, you derive an upper bound on this quotient. So derivative of your ground state divided by the ground state. And remember, the ground state is strictly positive. So you don't divide by 0. So you derive an upper bound, and you derive an upper bound in terms of the L1 norm of V. So this is the first part of the proof. And then as soon as you have this, you define this function f of t, which is the logarithm of the ground state with shifted arguments. So you see for t equal to 0, you have phi naught at y, and for t equal to 1, you have phi naught at x. And then you can imagine you have like, you can express f1 minus f0 as the integral over f prime from 0 to 1. So in a way, you differentiate this expression. And if you do this, then you suddenly, this term appears, right? And then you simply estimate this integral. You use this bound. Then you obtain this extra factor of L, and then you exponentiate. And that's how you end up with this factor here. Okay. So this is how you arrive at Harnack's inequality. And now it's very simple. You just combine this Harnack inequality with this result of Kirsch and Simon, and then you arrive at this lower bound. And so again, the good news is this lower bound is general, so it holds for all bounded potentials. I mean, non-negative, of course, and for all values of L. I mean, the bad news is it's a very small lower bound. I mean, it decays at least exponentially. I mean, if the potential is in L infinity, but not in L1, so this might also diverge like L. So you have e to the power minus L squared. So it's very small, but it's very explicit. So you can calculate it. And let me just say one thing, two more things. So of course, the factor of 8 here certainly is not optimal. So you can improve on the number 8. But something which is a bit more not so clear is, for example, once I was giving this talk and I was asked, like, so this, it seems to me, the guy said like that this L1 norm should be enough. Like it contains information about the volume. So maybe the factor of L shouldn't be there. But this is, I mean, this cannot be the case because we know that, for example, if L wouldn't be there, and for example, if you have a compactly supported potential, this would be just a constant, right? So you had a lower bound, which is the constant divided L squared. And we know this cannot be the case because we know the gap, at least for Dirichlet boundary conditions, converges to 0 faster than 1 over L squared. So you need something extra that decays to 0. Okay. Okay, again, the bound is, it's general, but it's weak. So, and you remember we had the small conjecture. For example, for compactly supported potentials, we expect that the gap goes to 0, like 1 over L to the power 3. So this bound, of course, is very far away. So what do we do? So we want to improve on this bound. And this is possible. But for in order to do this, I had to restrict the class of potentials. So what do we do? So again, we are on the interval with Neumann boundary conditions, bounded non-negative potential. And now we impose some restrictions on the potential. So for the first time, we assume symmetry. And we assume that the support is the interval minus b to plus b. And then we have two extra conditions. Let me start with this condition here. This is a sort of a weakness condition. So assuming the support is fixed, the L infinity norm cannot be too large. And this condition here tells us that the potential is bounded away from 0. Maybe now I can go to, okay, and you tell me. Yeah, okay, that's fine. So basically what we assume here, we have minus b, and then we have a potential which, for example, might look like this, okay? So it's allowed, it may oscillate or do whatever it wants, but it has compact support. So this would be a proper potential. It's actually possible. You don't need this bounded away from 0. You can also assume that it's like monotonically increasing up to a certain level, and it has to be symmetric, of course. So this is also possible here. But you want it to be monotonically increasing in a small interval here, and then stay away from 0. So what you want to avoid is you don't want the potentials to look like this, okay? So oscillating down to 0 all the time. So this is what I don't want. Okay, now I go back to my slides. And I hope you see the slides, yeah. Okay. Okay, thanks, yeah. Okay, so now what can we show for such potentials? So now we can prove a lower bound, which is of this form. So you can prove that the spectral gap cannot converge to 0 faster than constant divided L to the power 4. And so as you can see, this is of course much better than this bound. The downside is, in a way, I mean, it's only true, this holds for only L large enough. And of course, you have a limited class of potentials. And in a way, of course, I won't go into the proof here. So these conditions seem a bit obscure, but still you need them all. So for example, the symmetry condition implies that the ground state is also symmetric. And this, for example, leads to the fact that the derivative vanishes at 0, which you use at some point. Then this weakness condition simply comes from the fact that, well, what you do is let me just say, so I again use this Kirchhoff-Simon result. But instead of using a Harnack inequality, the idea is to, in a way, directly say something about this quotient for such potentials. And by doing this, you obtain a lower bound which contains a factor 1 minus 2b squared times L infinity norm of V. And I mean, it's a lower bound, but in order to be a useful lower bound, you want this factor to be positive. This leads to this weakness condition. And then this condition here has to do with turning points. So, I mean, if you look at the eigenvalue equation, you can view it as an equation for turning points, right? So the second derivative is 0 whenever the eigenvalue equals the potential. And then if you have the potential, we know that if you increase the volume, the eigenvalue converges to 0, right? So if you have a potential like here, the one we allow for, then at some point the eigenvalue is very small. So here and here something happens. So the second derivative changes sign here, but it doesn't change sign anywhere else. And this is basically what we use. And if you have a potential of this sort, it's difficult because you have things happening like many times. So this is just to give you an idea of why we use this condition. So this is about turning points, and this has to do with simply a lower bound being meaningful. Okay. And now let me move on to higher dimensions. Yeah, and we start with 2 dimensions. And this now is work together with Matthias Teuffer from Hagen. And so now we work on a square of side length L, and we have a potential, again, of course, non-negative, bounded, but on R2. And we are also back to Dirichlet boundary conditions. There's no specific reason, but we simply chose Dirichlet boundary conditions. And now we have the same question. Okay, we have a spectral gap. What about upper and lower bounds? And remember also we had this peculiar effect from one dimension. So as soon as, like in one dimension, you have a compactly supported potential, and then the gap converges to 0 strictly faster than it does for the free Laplacian. And our question was, of course, what happens in 2 dimensions? So is this effect still present or not? So the first remark is the upper bound is easy. So again, we have an upper bound for fast decaying potentials, which goes like constant divided L squared, simply because you increase the volume and your 2 eigenvalues converge to 0 like 1 of L squared. So what about this decaying fastest to 0? And this, yeah, again, maybe surprising. The answer is it disappears. So this effect that we've discovered in one dimension doesn't exist in two dimensions. So in other words, for fast decaying potentials, you can prove a sandwich theorem of this form. So you have upper and lower bounds which go to zero like 1 over L squared. And this has a nice intuition behind it. Okay. Okay, so let me just do it here. So let's say now we have a square, right? Now here somewhere we have a potential, the support of the potential. And so now you increase your square. So you see here you have the potential sitting. So and this again creates in a way a Dirichlet point. A Dirichlet point. But now the difference is in the one-dimensional setting you create a Dirichlet point, but this cuts your configuration space into two parts. Okay, but in two dimensions this is not the case. So you have a Dirichlet point, but you don't cut your domain into two or more pieces. And this is intuitively the reason why you lose this effective degeneracy of the ground state, right? I told you this, you have two ingredients, increase of volume, we have in both cases, and that's why the gap converges to zero, at least like 1 over L squared. But in the one-dimensional setting, you have this extra ingredient of an effective degeneracy of the ground state because of the Dirichlet point. But this you miss in the two-dimensional setting because you don't have this effective degeneracy of the ground state. Okay, so from an intuitive point of view, it's not surprising that you have this result. So let me just mention a bit more like mathematically what's going on. So what you do is from first of all, you do a rescaling of your operator, and we do the same thing in one dimensions. So you have a unitary transformation. You go from your interval of length L or square of length L to a fixed configuration space. And the price you have to pay is that now the potential depends on L. Let me just go back here. So you see, if you do this rescaling, that you obtain a potential VL, and this is given by this. So it's L squared times your actual potential at argument L times X. And now you see what's going on. So if you increase L, now you're on a fixed interval or fixed square, this potential becomes larger and larger, and the support shrinks to zero. And in this way, you create, like in a rigorous sense, you create a Dirichlet point. Okay? So whenever I spoke of a Dirichlet point, this was the thing I had in mind. You had the rescale potential, this goes to infinity, and the support shrinks to zero. Okay. Okay, so you do this rescaling, and then you use a nice result of Osawa. And Osawa looked at nice enough domains and who have that have holes. So if you have a domain which that has a hole, whose diameter shrinks converges to zero, then Osawa proved that the eigenvalues converge to the eigenvalues of the domain without the hole. So, and we use this result. So we cut away so we know we have the potential that shrinks to zero. We cut it away. We use like operator bracketing techniques. And then we have, Osawa tells us that the eigenvalues converge. And then using this, we can prove this lower bound. So in other words, I mean, so in two dimensions, Dirichlet points don't matter. And this is rigorously shown by Osawa. And this for us means that compactly or fast decaying potentials disappear. Like you don't see them in the asymptotics of the gap. Okay. And now let me finish with, not finish, but let's say, what about higher dimensions, okay? And the funny thing is, so in one dimension, you have this surprising effect of faster decay of the gap. In 2 dimensions, this effect disappears, but it's not so simple to prove it disappears. I mean, you use Osawa, and Osawa is not so easy to, this result is not so simple. So it's quite difficult still to prove it, all in all. But quite funny, it's very simple in higher dimensions. So for example, if you look at potentials in L infinity and L1 in at least 3 dimensions, then I can show you in 5 lines that you have this sandwich, okay? I mean, the upper bound is clear anyway, so let's focus on the lower bound. So now you are on a d-dimensional cube with Dirichlet boundary conditions, right? So you know the eigenstate explicitly, you have separation of variables, so you have a product state, it's normalized. And you also know the eigenvalues of the free Laplacian. So for example, here, this is the second eigenvalue of the free Laplacian. And since you add a non-negative potential, you certainly have this inequality here. Each eigenvalue goes up, or at least doesn't go down. Okay, so you trivially have this inequality. Then you look at the ground state eigenvalue and you employ the variational principle, which tells you, okay, this is smaller equal to this. I mean, it's equal here. And then you simply plug it in, and you have the kinetic part, which is this, and then you have your potential part, and then you simply estimate this integral. You pull in front the L infinity norm of your ground state. Okay, and here you have the L1 norm of the potential, which is just some number. And the key point is, if you look at your ground state, the L infinity norm squared behaves like 1 over L to the power D, okay? So if you are in 3 and more dimensions, this is of a lower order, okay? And then now you can subtract this from this, and you immediately conclude that the spectral gap has this lower bound, okay? It's a lower bound. I mean, you have to think about it, because here you have a lower bound on the second and an upper bound on the first, and this gives you a lower bound on the gap. So, and you immediately see this phase transition in a way, right? So for d equal to 1, this doesn't work, because this is dominating. For d equal to 2, they are in balance. So it works for small L1 norms, so to speak, but not for all potentials, trivially. So this is somehow, it's not clear what's going on, but for d and higher dimension, for 3 and higher dimensions, the potential term simply doesn't contribute of means of a lower order. Okay, so, and now let me just finish by saying, like, okay, so this has been disappointing in a way. So it seems that in higher dimensions, this effect, like of a gap converging faster to 0, disappears. But actually, no, you can recover this effect. So the question is it possible to construct a potential for which, again, you conclude that L squared times the gap is 0, converges to 0? And the answer is yes. And maybe it's a picture is the best way to show it, if I can do it. Yeah, let's do it here. So this is the square. And you remember, like, here it didn't work, right? Because if you have like, say, a compactly supported potential, this will shrink in the rescaled version of the operator and will create just a Dirichlet vertex. Yeah, Dirichlet point. And a point you don't see in 1 and 2 dimensions. So now what you have to do, obviously, is you have to start with a potential that is supported maybe, for example, on a strip, okay? And if it's supported on a strip and you do the rescaling, what happens is you create a Dirichlet line, right? So again, you cut your configuration space into 2 parts. And then you have, in the infinite volume limit, again, you have a degeneracy of the ground state, because in a way you have the ground state from the left-hand side and you have the ground state from the right-hand side. And they Yes, and so in a way, your ground state of the actual thing decomposes into these two eigenstates. So it's the same intuition, and I mean you can prove it. I mean rigorously, and the basic idea is the same as in one dimension. That I mean there are some technicalities, but still okay. So that's all I wanted to say. So thank you for your attention.
Thank you, Joachim, for the nice talk. Are there any questions by the audience? If you have any, please raise your hand, and then I will give you a possibility to speak. Okay. Julie, please.
Thanks, Joachim. That was sort of perfectly explained what's going on there. Do you think your results in 2 dimensions for the cube would just hold generally for a compactly supported potential on a general convex domain?
Yeah, absolutely, yeah.
Yeah.
So these, yeah, so basically, yes, because what's going on, like on any domain, it doesn't have to be a square or a cube. You have this potential shrinks to a Dirichlet point, right? If you have a compactly supported potential. So in other words, so the only problem is we use the Osawa's result, right? Which and that result compares a domain with a hole with the domain without a hole. So it compares the eigenvalues. And Osawa uses, I think he assumes smooth boundary. But if you think that, like, assuming Osawa's result holds for like a general convex domain, then yes, because you would do the rescaling, you would have the potential would effectively shrink to a Dirichlet point, and then I would expect definitely to have the same result. Yeah. But maybe Matthias, I mean, Matthias is also here, but I think so, right? Is this what you asked?
Yeah, that's exactly what I asked. Thank you.
Yeah, so, yeah.
Julie, any further question?
No, that's exactly what I wanted to know. Thank you.
Good. Thank you. Any other one? Any other questions or comments? No? Okay. I have one question. Can you, so when you go to your Hanach inequality, or this result by Kirsch and Simon, so the problem is actually basically that you don't get a sharp bound basically from this Hanach inequality. So I think this is the max and the min. I think that you need basically the information of the maximum and the minimum of the first ground state, of the ground state, that probably causes you trouble. Is this right, basically, in your convergence results?
Like trouble in terms that it's not sharp or something?
Yeah, that you don't get sharp bounds, basically, yeah?
Yeah, definitely. I mean, I mean, absolutely. I mean,
alone that you have to fight basically with the L times the norm, the L1 norm of the potential. I mean, I think this is not leading. Yeah. So I mean, you don't get sharp bounds, and then if you would find a way to get sharp bounds, then yeah, you get.
Yeah, definitely. It's just so I think from a certain point of view, I would think that, like, I mean, this is a nice result, but I guess to start with, this is maybe I don't know if this is good to start with, you know, this lower bound anyway. So yeah, definitely. I mean, it's not clear. For example, you would something which is not clear is also like, can you construct, I mean, yeah, okay. Yeah, I mean, definitely. What can I say? I mean, it's true. But if you, let's say, if you assume this conjecture somewhat correct, then it's obvious, right? So you would have that the lower bound is something like 1 over L to the power 3. So this is far, far away, right?
Mm-hmm.
But also here you don't have decay conditions, right? So for example, for this effect to happen, you need fast decaying potentials.
Mm-hmm.
So if you have like potential that decay like 1 over x, it's not clear what's going on. This is a very weird scenario, actually, regime. If you, yeah, it's, so there's a sharp phase transition going, like if you have potentials that decay like 1 over x squared, everything is fine. This is the borderline case. If you have slower decay, the whole technique that we use seems to, I don't know, fall apart in a way. And so what I want to say is that this bound really, I mean, it's not necessarily related to this other stuff. It means just because here you don't have decay conditions, anything. I mean, here you can also have like periodic potentials or oscillating or things like this, right? So I agree. I think it's not at all clear if it can be close to. So I would be interested, is there potential like, so that you have a lower bound which at least looks a bit like this, you know? I'm not sure. I'm not sure. But yeah. But I found it interesting because it's very explicit, right? And usually when you have Harnack inequalities, you have, I mean, you don't know the constant, right? You know there is a constant, and it depends on all you know parameters like potential, volume. So and now as soon as you start, the problem is you have a Harnack inequality, and that's all fine. But now remember, we want to play with the domain. You increase the domain.
Sure.
And then you don't know what to do because you don't know the constants. So you're stuck in a way.
Yeah, sure. No, I understand. It is a, yeah.
So
it gives you at least something on the L, yeah.
Yeah.
And that's something. So one other question I have is, okay, you are now always focused on this multidimensional square. So what happens if you take any other convex set and you would play then with a diameter? It should basically also similar separation phenomena, which you discussed, which you have in the center, should occur or not? Or what do you think, Joachim?
So it's like related to Julie's question. So I think so, yeah. I mean, so we chose a square for convenience because so where the problem came from, you would choose a square. You can definitely work on other domains. But I mean, the separation of, you don't need the separation of variables. I mean, you can prove this is a variational result. Yeah, so in principle, of course. Yeah, so yes. I mean,
well, you used a little bit that you have that phi naught is explicitly given by one of the bounds. I mean, so one bound is you use that you know exactly the value of the eigenvalue. Yeah.
Like in this, yeah. I mean,
yeah.
Like you mean here, right?
Yes.
But basically, I mean, you have the thing is, I mean, as soon as you have, if the ground state is non-degenerate, so you know that this doesn't equal to this in a way, right? So so you don't really have to know them, right, explicitly. So you know that this is strictly larger than this. Yeah, and this is of a lower order. So I guess So yeah, I mean, the only, so assuming the first and the second eigenvalue go to 0, like at the same rate, which, I mean, certainly you can construct weird, I mean, the thing is, it matters how you do the limit, right? How you blow up your domain, for example.
Mhm.
But if you do it just by translation, like we did, I think it should be somewhat fine, yeah. But there are, when you can blow up a domain, like, and you blow up one direction less than the others, things like this,
Mhm.
And then things are different, of course, because then they are not of the same order.
Mhm.
So yeah, okay.
Okay, maybe let's thank the speaker again for the nice talk. And you see in the chat there are already the Zoom details for those who didn't receive already an email. So every one of you is invited now to a coffee break. And please join us. And you can also ask some informal question how the weather is currently in Germany or in Wuppertal. And yeah, so thanks, Joachim, again. And
Okay.
I would close the session and hope you come also to the coffee break. Thank you, everybody. Bye.
Bye.